Hello and welcome to this video. In the next 5 minutes, I will present you a demonstration entitled Multi-Armed Bandit Learning for IoT Network, or MALIN for short. We presented this demonstration at the ICT conference in Saint-Malo in June 2018. It is a joint work between Bonnefoi, Besson and Christophe Moi. Here in this picture, we see Rémi operating the demo. Nowadays, a lot of new objects are using wireless communication for what is now called the Internet of Things. They usually use unlicensed bands, and a lot of new objects are using the same bands, causing a discrepancy in the spectrum. In such context, we are looking for solutions to allow the coexistence of devices in order to reduce the interference. In our demonstration, we generate some random traffic, and we control an intelligent object. This object will use reinforcement learning algorithm to learn to improve its communication and use the most free spectrum channel. We are using real-world hardware and 3 components. One is a noise generator, one is an intelligent object, and one is a gateway. As we can see here on a spectrum analyzer, we are using 4 different channels on the ISM band located at 433.5 MHz to communicate both for the noise or the random traffic and for the communication of the object and the gateway. The goal of this first device is to simulate some random traffic in the 4 channels. A few channels will be more free than the others. The second box is the IoT object, and it will try to learn to use the most free channels. It can do so by sending and receiving message to and from the gateway. Every 3 seconds, it sends a short message, and if it's received without collision and without interference, the gateway replies with an acknowledgement. Let me present the 3 components in the user interface of our demo. The first one is a random traffic generator. It sends data in a few channels. The first few channels are more busy than the last 2 ones. The second component is a user interface for the object. In the waterfall on the left, we see the emissions. In the waterfall on the top right, we see the reception and the emission. The red indicates the sending message, and the green is an acknowledgement. And on the bottom right, we see a few charts. The first one in red shows the trials in each channel. The one in yellow is a success, and the one in blue is a mean success. As expected here, the first 2 channels have been tried less and are way less efficient than the last ones. The last component of our demo is a gateway. Here on the top right, we see the waterfall of the received signal in the gateway. It observes the traffic from the random generator, the input message from the user, and we see in red the output message or the acknowledgement. When we put together the 3 parts of our demo, it looks like this, or, to zoom a little bit, like this. For a real-world application, an IoT device has to minimize its battery consumption. Here, the goal of the object is to communicate once in a while and learn which channel is the best. That means which channel is the least occupied by the random traffic. When we model this mathematically, the object is facing a discrete time, discrete action, decision-making problem, also known in the literature as Multi-Armed Bandit. The user is facing n channels, here 4, and his goal is to learn to identify the best channel. Our demo is a proof of concept that multi-armed bandit learning can be useful for IoT communication. Here, we are controlling the random traffic, and we are asking every channel to follow a Bernoulli distribution of a different mean. The goal is to identify the best channel, or the channel with the highest mean. The algorithm we use for this is called UCB for upper confidence bound. Actually, it's quite a simple algorithm, and real-world hardware can implement it for real, with really low capability of computation and storage. As shown here, we only need to do a small computations. The name comes from the analogy of playing a one-armed bandit in a casino. Let me conclude by showing you some example of results. Here, we are saying that the noise is really present in the first 2 channels, and the object has learned to avoid them. He is mainly using the last channel, as we can see on the red plot. In this second example, I change the distribution of the traffic. There is less battery-batching traffic in the channel number 2 and 3, and as we see here on the red plot, the object has learned to focus mainly on the channel number 3, the most free. If you focus on the waterfall in the middle, you can see that some message has not received a knock. For instance, the first red message has not been received by the gateway, and so no acknowledgement has been sent. For the last example, I would like to highlight that our demonstration is only using something called as software-defined radio. We are using the GNU Radio software for every part of the demo, the UI and the hardware, which means everything is easily configurable. Here, during the conference, on live, I changed the demo to use from 4 channels to use 8, as we see here. Similarly to the first example, there is a lot of background traffic in the first few channels. and as we see on the red plot on the chart, the object has learned to mainly use the last channels. Interestingly, it's not focused on only one channel, it has learned to use the last two ones most of the time. And as we can see here, it has started to be in a sequence of using the sixth channel. To highlight the efficiency of the learning algorithm UCB, we can show here the difference in successful transmission rate between a random user and a user using UCB. Obviously, if the channel occupancy rate is not completely uniform, then the learning can be useful. You can find the list of references in the description of this video. The first reference is our paper presented last year at the CROWNCOM conference, and the second one is the source code of this demo, released under the GPL license. To conclude, thanks a lot for listening to this video, and we stay at your disposal if you have any questions. Thanks!